The first law of thermodynamics. The first law of thermodynamics is an energy conservation equation. It simply says that energy is conserved. And it's written as du, the change in the internal energy, as the sum of the heat gain or loss, del Q, plus the work done by the gas, del W. Consider the system shown. A certain amount of heat can be added or subtracted, del Q, and work can be done by the system in expansion or contraction. When the work is pressure work only, we can therefore write this equation. The first law is du is equal to del Q minus PdV. Remember, du is the internal energy, or the change in internal energy rather. So imagine the volume staying fixed. The change in the internal energy will simply be a function of the heat added or lost. In the case shown, del Q is positive, there's heat added to the system, so the internal energy must increase. And that will be expressed in the random motion of the molecules inside, translational, vibrational, etc. Now consider the case where there's no heat added to or lost from the system, but the system expands as is shown. Since dV will be positive, the volume increases, minus PdV is negative, that is, the internal energy of the system must decrease. In other words, the work that the gas is doing on the environment is taken from the internal energy. We can write the first law in terms of the enthalpy. Remember, enthalpy, H is written as U, the internal energy, plus PV. So changes in H, dH, is equal to changes in the internal energy, du, plus changes in the product, PV. The internal energy can be expressed as shown there in terms of the first law, del Q minus PdV, and dPV may be expanded using the chain rule, PdV plus V dP, so that you get the two middle terms cancelling, and the first law in terms of changes in enthalpy dH is equal to del Q plus V dP. Now for an ideal gas, U, the internal energy, and H, the enthalpy, are only functions of temperature. So we can measure the changes of those in the lab, and du, the change in internal energy, is equal to m by this constant Cv by dt, changes in the temperature, and the change in the enthalpy dH is equal to m, the mass, by a constant Cp, multiplied by dt, changes in the temperature. Cv and Cp are approximately constant and are properties of the particular gas that we're considering. Cv and Cp are called specific heat capacities, and they're measured in units of joules per kilogram per Kelvin. Since we might write du is equal to mCv dt and expand that as del Q minus PdV, if we keep the volume constant, then du is equal to del Q. So the change in internal energy is simply the amount of heat that we add, and by the equation, del Q is equal to mCv dt. So as we can see in the illustration on the right, we have a piston where the volume is not allowed to change, and so changes in the internal state are simply related to the amount of heat that we add. So Cv is a measure of the amount of heat you have to supply to a system when you hold the volume constant to increase its temperature by 1 Kelvin for 1 kilogram of the substance. If we then allow the volume to change inside our piston such that dP is equal to 0, then the change in the enthalpy dH is equal to mCp dt, which is equal to del Q plus V dP, but dP is equal to 0, so that's simply equal to del Q, so we can write del Q is equal to mCp dt, which means that Cp is a measure of the amount of heat you have to supply to a system holding the pressure constant to increase 1 kilogram of the substance by 1 degree Kelvin. We can relate the gas constant now in the specific heats by noting that dH, the change in the enthalpy, minus du, the change in the internal energy, may be written as m outside of Cp minus Cv by dt. But we can also write dH minus du as d by h minus u, which is equal to d of PV, using the definition of enthalpy. And hence for ideal gases we can write dH minus du is equal to d mRT. So that's just replacing PV by mRT using the equation of state, or the ideal gas equation. And so that's dH minus du is equal to mR dt, which we can equate with the equation up the top, and hence we can relate the gas constant R to the specific heat capacities. So R is equal to Cp minus Cv for an ideal gas.